For video 2 here, we're going to do derivation. This is what physicists do to write equations. This is how they come up with these equations that we're using. This is something that I wouldn't expect you to be able to do on a test, but it's important to understand that we're not getting these equations from nowhere, and so that's why we're doing this derivation. So here's what it says. Starting with the definition of acceleration, prove that impulse is equal to a change in momentum. So here's the definition of acceleration. They wanted us to start with this and prove all the rest of that. So basically what a derivation is you take something that you know is true and you make algebraic changes to it until you get this right here. So we haven't proven that this is a true equation, but we'll mess around with this. Yeah, that's basically what we're doing. We're messing around with this until we get that. So here's how we do this one. Maybe need another color. We're going to multiply both sides by m. So if I multiply both sides by m, just m, multiply the left side by m, multiply the right side by m, and we'll get something interesting. I'll rewrite it, make it nicer. So already we have something interesting kind of happening. When we multiply both sides by m, this right here is familiar. M times A is the same as force from an equation from before. If you take m times A, you get force. Specifically, you get net force. We're just going to keep it simple, though. We're going to go with F. So that's F. Over here, we also have something changing. We have m times v. Now, as we had on the previous page, I think I can put it back up here. We had on the previous page, P equals m times v. And by the same logic, a change in P is m times a change in v. So if I change the velocity of something, it changes the momentum. So that triangle part is a little weird. Well, just trust me that you can do it there. So what we have, I'm losing my track here. So we have delta P over delta T. So what happened was this is delta P, so I'm just writing it as delta P. This is a change in momentum. I feel like I should show that a little better. I can, yeah. So delta V is VF minus V initial. So if I distribute that in, we have MVF minus MVO. I think that's a little more clear. This is momentum final minus momentum initial. So there's how we're getting delta P. So don't worry about that part. Just kind of proving my thoughts there. And from here, we're pretty much at the end. We're trying to prove that impulse is equal to change in momentum. We have change in momentum right here, but we need to get impulse in there. As we saw on the last page, impulse is force times time. So why don't I rearrange this so that force is multiplied by time? What I'm going to do is multiply both sides by delta T. This is going to cancel out, and we pretty much got it. There's impulse. There it is. This is what we had on the last page. That is literally the definition of impulse. So we're there. I dropped my vector early on that P, but I'll put it back on now. So that's That's weird math, but that's what physics is. A lot of derivations, a lot of taking equations and inventing new equations. This is why people like Albert Einstein and Isaac Newton were considered so smart, because they could take crazy ideas like this and just internalize them and fly through and come up with new equations. So this is a lot of what physics is. If you even find that a little cool, you should consider taking some physics classes in college, maybe majoring in it. If that drives you insane, well, I don't know, it's tough, so maybe you should consider taking physics classes in college anyway. On to the final video, we'll do some examples. We'll get to some simpler math, some applications of the two equations.